Welcome to This Explainer. Today, we are diving headfirst into the deeply paranoid, wildly non-deterministic world of distributed systems. We're going to find out exactly how engineers actually manage to build highly reliable platforms out of parts that are, well, completely unreliable. So, if you've ever found yourself wondering why massive cloud services don't just instantly collapse under their own weight, you are definitely in the right place. All right, let's look at our map for today. We'll be hitting 1. The chaos of partial failures. 2. Networks and unbounded delays. 3. When clocks tell lies. 4. Quorums establishing the truth. 5. Leases and zombie nodes. And finally, 6. Fencing tokens and system models.
So what actually happens when your own servers start lying to you? We've got to start with this fundamental mystery. You see, in a single computer setup, things are relatively predictable, right? But the second you step into a distributed system, you cross this threshold where you absolutely can no longer trust your network, your clocks, or honestly, even your own nodes. It requires a complete, ground-up shift in how you think about software engineering.
Which brings us to part 1, the chaos of partial failures.
To really wrap our heads around this chaos, we first have to totally shatter that illusion of control you might be used to having over a single computer. When you write software for just one machine, it's deterministic. If a hardware problem pops up, like, say, memory corruption, the result is almost always a total system failure. You get a kernel panic, a blue screen of death, the whole shebang. It either fully works or it entirely crashes. But a distributed system? That introduces the nightmare of partial failures. This means some parts of the system will break in completely unpredictable ways, while the rest of it just blindly keeps running. You might try to do something across multiple nodes, and it might work or it might fail. And the kicker is, you might not even know if it succeeded. Non-determinism is literally the defining characteristic here.
Moving on to part 2, networks and unbounded delays.
Our very first betrayal in this distributed world comes from the exact thing connecting our nodes together, the network itself. And the threats to your network aren't just digital. Sure, you have human errors like misconfigured switches and software upgrades that can stall packets for over a minute, but get this. Wide-area fiber links have literally been taken down by cows, beavers, and no joke, sharks biting into submarine cables. Because we build on asynchronous packet networks, the network gives absolutely zero guarantees as to when a packet will arrive or if it's ever going to arrive at all. You just have to assume that network faults will happen.
So here's the really crucial point. Because of these unbounded delays, if you send a message and you don't hear back, you are left entirely in the dark. Did the remote node die? Was your request dropped somewhere along the way? Or is the response just trapped in some queue because a noisy neighbor on the network is saturating the link? Since there is no upper limit on delivery time, you have absolutely no way of knowing for sure. This is exactly why these systems rely on experimental timeouts, just to guess if a node is dead, even though those timeouts can so easily be wrong.
And that leads us to part 3, when clocks tell lies.
Now, if you can't trust the network to deliver messages on time, you'd probably think, well, I can at least trust time itself, right? Wrong. Clocks are notorious liars. Computers generally run 2 types of clocks. Time-of-day clocks return the current date and time, synchronized via NTP. But the thing is, they can drift, and if they get too far ahead of the NTP server, they can be forcibly reset. That means time-of-day clocks can arbitrarily jump backward in time. You should never ever use them to measure intervals. On the flip side, we have monotonic clocks. These act way more like a reliable stopwatch. They guarantee that time only ever moves forward, making them the much safer choice for measuring things like timeouts or response times in a distributed setup.
But wait, even if you use the perfect clock, time can still betray you through process pauses. Just imagine you're a node happily executing your code, and suddenly, you are completely frozen in time. This could be triggered by a stop-the-world garbage collection pause that lasts for seconds or, terrifyingly, even minutes, or maybe your virtual machine is in the middle of being live migrated to another host. During this freeze, the rest of the cluster just keeps on moving. They might even declare you dead, and when you finally wake up, you have absolutely no idea you are ever asleep until you actually check your clock.
Okay, part 4, quorums, establishing the truth.
Since nodes can be paused without even realizing it, and networks drop messages completely at random, an individual node really cannot trust its own judgment of reality. This quote vividly captures the absolute nightmare scenario. A node might think it is perfectly healthy, it's processing requests, it feels totally alive, but if the network is dropping its outgoing messages, the rest of the system simply can't hear it. To the rest of the cluster, that node is gone. And in a distributed system, that individual node just has to accept the group's decision and step down. So the only real way out of this detective story is to rely on a jury. Enter the quorum. A quorum ensures that even if a few nodes are lying, delayed, or disconnected, the majority rules and safely establishes the truth. Because a quorum strictly requires more than half of the nodes to agree, there can only ever be one majority at a time, period. If a quorum declares a node dead, it is officially dead to the system.
Which brings us to part 5, leases and zombie nodes.
But what actually happens when a node that the quorum declared dead suddenly wakes up from a process pause and still genuinely thinks it's in charge? This exact sequence creates a terrifying zombie node scenario. Often, systems use leases, which are essentially just locks with a built-in timeout to ensure only one node is writing to a file at any given time. But let's say node A gets the lease, and then suffers a massive garbage collection pause. Its lease is going to expire. The system safely hands that lease over to node B. But eventually, node A wakes up. It doesn't realize it was paused, checks its local state, thinks it's still the leader, and blindly attempts to write its data.
If we map out the timeline of this exact bug, a bug that actually happened historically in systems like HBase, is pretty wild. Client 1 gets the lease, but suddenly gets paused. The lock service then legitimately grants the lease to Client 2, which goes ahead and writes its data successfully. But then, the zombie, Client 1, wakes up and blindly fires off its write to the storage system. And the storage system? It doesn't know any better. It just allows the write, and boom, the file is permanently corrupted by this split-brain scenario.
Finally, part 6, fencing tokens and system models. To actually slay these zombie nodes, we have to inject a healthy dose of paranoia into our distributed locks using a really elegant, simple defense mechanism. Fencing tokens. They act as an absolute barrier. Every single time the lock service hands out a new lease, it also hands out a token, which is just a number that goes up every single time, 33, 34, 35. The storage server keeps track of the highest token it has ever seen. If a zombie node wakes up and tries to write with an older token, it becomes instantly obvious that they're an imposter, and the write is immediately blocked.
Let's see this brilliant mechanism in action. Client 1 gets paused while holding token 33, Client 2 then takes over with token 34 and writes to the storage node. The storage node remembers, okay, the latest is 34. When our zombie Client 1 finally wakes up and attempts to write with token 33, the storage node just looks at it and says, nope, no way, I've already processed token 34, you are way out of date, and safely rejects the write. Disaster averted, data corruption prevented.
To properly test for all these nightmares, engineers have to model reality as accurately as possible. You really can't just assume a simple crash-stop model where nodes cleanly die and stay dead forever. You have to design for crash recovery, where they actually reboot and come back. And maybe most insidiously, you absolutely must account for limping nodes or fail slow scenarios. Think about it. A node whose network interface drops to an absolute crawl because of a weird driver bug is often far more dangerous and way harder to detect than one that just completely unplugs. To make sure everything works under these hostile models, engineers heavily rely on fault injection and deterministic simulation to constantly test their assumptions against the chaos.
Ultimately, what this whole explainer shows us is that in the world of distributed systems, hope is simply not a strategy. You cannot hope the network is fast, you cannot hope your clocks are perfectly synchronized, and you certainly can't hope your nodes won't just pause randomly. But by embracing suspicion, by specifically designing for these inevitable betrayals using majorities, quorums, and fencing tokens, we can actually build highly reliable systems out of inherently unreliable components. So the next time you sit down to design a system, you have to ask yourself, are you designing for the happy path, or are you designing for the chaos?